Welcome to The Explainer. Today, we're going to crack open the Linux kernel's cryptographic toolbox. We'll take a look inside to see how it uses one of the most fundamental tools in all of digital security, the hash function.
So, here's a question for you. How does Linux know that the software you're running is actually the real deal and not some imposter? It's a super important question, right? Well, the answer lies in this really powerful idea called cryptographic hashing. It's a process that creates a totally unique digital fingerprint for any piece of data, which guarantees that it's authentic and hasn't been messed with.
Here's a way to think about it. A hash function could take, say, this entire explainer script and just crunch it down into a single, unique sentence that represents the whole thing. Now, you can never get the full script back from that one sentence, but if you change just one single letter in the original script, you'd get a completely different sentence. That right there is the power of a one-way function. And this is where it gets really cool, because these digital fingerprints can do two different jobs. A simple digest just checks for data integrity. It basically asks, hey, has this file been accidentally corrupted? But things get way more interesting with what's called a MAC, or Message Authentication Code. By mixing a secret key into that recipe, it answers a much bigger question. Is this data actually from the person who sent it, and has anyone touched it?
Okay, let's dive into the kernel's toolbox. Now, it might actually surprise you to learn that it's still holding on to some older tools, the kind that are now considered insecure for most of the really critical security jobs. So why on earth are they still in there?
And this is a perfect example of that right tool for the right job idea, even if the tool is a little bit rusty. MD5. It's famously insecure these days because of something called collision attacks. That's where a bad guy can create a malicious file that has the exact same fingerprint as a legitimate one. So, why is it still in the kernel? Well, it's used for things that have nothing to do with security, like generating TCP sequence numbers. In that case, a collision isn't a catastrophe, and its blazing speed is the only thing that really matters.
You know, the story of SHA-1 is just a fantastic case study in how all this stuff evolves. It used to be the absolute king of hashes, but its decline was a long time coming. And here's the detail that really tells the story. It was proven to be completely broken, in practice, back in 2017. But the Linux kernel only switched its default for signing modules away from it this year, in 2024. That just shows you the sheer inertia, the amount of work involved in updating a project as massive and as important as the kernel.
So the big takeaway here is that the kernel community is always doing security hygiene. They're constantly, actively phasing out these older tools. A perfect real-world example is Lux, which is the system that encrypts your hard drive. It has officially dropped the old RIPMD 160 algorithm and is now using the much stronger SHA-256. That means your data is literally safer today than it was yesterday.
All right, so enough about the old guard. Let's talk about the modern workhorses, the algorithms that are out there protecting you right now, every single day. The current powerhouse is, without a doubt, the SHA-2 family of algorithms. I mean, this thing is the absolute bedrock of modern Linux security. It's protecting your data at every single stage. When your data is just sitting on your hard drive, Lux is using it for full disk encryption. When it's flying across the internet, IPsec uses it to secure that connection. It even guarantees your files haven't been touched with FS-Verity and make sure your kernel modules are legit. It really is the kernel's go-to security tool.
So how does the kernel use these hashes to actually prove authenticity? Well, the secret sauce is this little recipe called HMAC. By mixing a secret key, something only the sender and the receiver should ever have, into the hash calculation, you create a fingerprint that simply cannot be forged. Only someone with that same secret key can create it, proving the data must be from a trusted source. Pretty clever, right?
And this chart just gives you a sense of how foundational these modern hashes really are. They're not some optional add-on feature. They are woven directly into the kernel's core security model. They're protecting your most critical data, from the files on your disk to the packets on your network.
But, and here's a really interesting twist, the kernel's toolbox is not just full of these cryptographic hammers that are designed for security. It also has some highly specialized instruments that are built for one thing and one thing only: pure, unadulterated speed.
I mean, this quote just says it all, doesn't it? Sometimes you don't need the security of a bank vault, you just need a really, really fast way to sort and find things deep inside the kernel's complex data structures.
And this is such a critical distinction to make. An algorithm like XXHash is not for security. You would never, ever use it for that. It's used in these performance-critical areas, like the BPF system, to organize data in what are called hash tables. Think of them as super-fast digital address books for finding information in an instant. In that situation, security isn't the goal. Raw, RAM-level speed is absolutely everything. So, okay, we have all these different tools. Old ones, new ones, secure ones, and super-fast ones. How on earth does the kernel possibly manage this huge, constantly evolving toolbox?
Well, it's actually a remarkably sophisticated system. You've got the crypto API, which acts like the central dispatcher. Any part of the kernel that needs a hash function, just ask the API and it gets the best one available. Then there's kconfig, which lets builders customize the kernel, maybe for something small like a home router, stripping out hashes they don't need to save space. And finally, the whole thing gets this massive speed boost from hardware acceleration, which uses special instructions built right into modern CPUs.
And this focus on maintenance really shows us the kernel's strategy for the future. The developers are embracing what's called crypto agility. They're adopting algorithms with totally different designs, like SHA-3, just in case a major flaw is ever found in the SHA-2 family. They're specializing with non-crypto hashes for speed, and, maybe most importantly, they are absolutely committed to actively deprecating old tools. It's a never-ending cycle of improvement.
And that is really the key takeaway here. The battle for digital security is a moving target. Today's workhorse is always tomorrow's legacy algorithm. The kernel's cryptographic toolbox is never truly finished. It's in a constant state of being sharpened and restocked for whatever challenges are coming next. So it makes you wonder, what will the next generation of digital fingerprints actually look like?